In this section, we're going to talk about hyperbolic functions. This is not an AP topic, and it's not in our book. It's not something that we're going to make a big deal of, and I'm not going to ask you a test question on it. This is more along the lines of just exposure or introduction to it. So if you do see it somewhere, at least it won't be completely out of the blue. So we have this thing, this SINH of x, which is the hyperbolic sine of x, and it's sometimes referred to as sinh of x. And it has nothing to do with sines or cosines at all. In fact, it's e to the x minus e to the negative x all over 2. So it has to do with the difference of two exponential functions. And the hyperbolic cosine of x, which is sometimes referred to as cosh of x, is e to the x plus e to the negative x over 2. And in a similar fashion, you can define the other hyperbolic functions, the hyperbolic tangents, and these are all defined in terms of hyperbolic sine and hyperbolic cosine, just as the trig functions can be defined in terms of sine and cosine. So hyperbolic tangent is hyperbolic sine over hyperbolic cosine, and likewise there's hyperbolic cotangent, hyperbolic secant, and hyperbolic cosecant. The name is kind of interesting. The name comes from comparing the area underneath a semicircle. That's the function y equals the square root of 1 minus x squared. So if you take the integral from negative 1 to 1 of the square root of 1 minus x squared, we can actually do this integral. It takes trig substitution, and it's a little bit involved, but we could certainly do this, and you get this 1/2 times the quantity x square root of 1 minus x squared plus the arcsine of x. And then in another integral that's so similar, the integral from negative 1 to 1 of the square root of 1 plus x squared, which geometrically is the area underneath one branch of a hyperbola. That hyperbola y squared minus x squared equals 1. And if you integrate that from negative 1 to 1, you get this 1/2. It looks almost just like the answer we got to the area underneath the semicircle is 1/2 x times the square root of that 1 plus x squared plus, and then what's called the inverse hyperbolic sine of x, which again isn't going to look anything at all like a sine or a cosine. In fact, if you try to start with your definition of a hyperbolic sine, e to the x minus e to the negative x over 2, and try to solve for its inverse, like you did in your AP Prep in your Algebra 2 days, switch the x and y and solve for y, you eventually get that the inverse hyperbolic sine is, of course, has a logarithm in it, so it doesn't look anything like sines or cosines. Anyway, that's where the name comes from. Now, there's this important fundamental relationship, just like we have in trig. In trig, it's sine squared plus cosine squared equals 1. With hyperbolic functions, it's the hyperbolic cosine squared minus the hyperbolic sine squared is equal to 1. And you have great derivatives. So the derivative of hyperbolic cosine is hyperbolic sine, and the derivative of hyperbolic sine is the hyperbolic cosine. So there's no sign change at all, like there is with the derivative of just sine and cosine. The graphs are kind of worth looking at a little bit just for a little understanding. So notice that the hyperbolic sine, because you have e to the x minus e to the negative x, when x is 0, you're going to get 0. So the graph of hyperbolic sine is going to go through the origin. And if you kind of consider the limits as x goes to infinity, as x gets really, really big, that e to the negative x is going to get smaller and smaller, and it's going to become more and more insignificant, and the graph is going to look more and more like y equals e to the x over 2, which we know what that looks like. That's an exponential growth function. So that's what the hyperbolic sine looks like as you go further and further out there to the right. Likewise, as x goes to negative infinity, then what happens is that e to the x part is going to go to 0, but the negative e to the negative x is going to dominate. And so because of the negative part, it's going to look like a reflected exponential decay curve. And that's going to, then our hyperbolic sine curve is going to approach that asymptotically. It's going to get closer and closer to that. So it looks kind of like a swirling motion there as it goes through the origin. Kind of reminiscent of a cubic, but not exactly, because it's exponential, so it's going to get steeper quicker in both directions. The hyperbolic cosine is going to be kind of reminiscent of a parabola, but again, much steeper because it's really exponential. And so you can see, again, as x goes to positive infinity, as you put in really, really big numbers, the e to the negative x is going to become insignificant, and the curve is going to look more and more like that kind of right side of our exponential growth function. And as x goes to negative infinity, then the e to the x part becomes insignificant, and the e to the negative x is going to dominate, and so our curve is going to approach more and more that reflected exponential growth curve. So that's what we're looking at. So let's slide down here and do just a little bit of calculus with it. We're not going to get too carried away here, but here's a little chain rule derivative. So the derivative of hyperbolic sine is hyperbolic cosine, and it'll be of that same inside function, and then we'll just take it times the derivative of the inside function, as we would with any other chain rule derivative. And so we'll just get 6x times cosh of 3x squared plus 4 is our derivative. And in the middle one, the yellow function, we are going to go 1 over u du. So we'll get the hyperbolic cosine of x will go in the denominator. Its derivative, du, will go in the numerator, and that's just the hyperbolic sine. And you may recognize the hyperbolic sine over the hyperbolic cosine is the hyperbolic tangent. In the green one, we're going to get a little product rule. So we're going to get the first x times the derivative of the hyperbolic sine, which is hyperbolic cosine, plus the second function, hyperbolic sine, times the derivative of x, which is 1, and then minus the derivative of hyperbolic cosine, which is a hyperbolic sine. And we can see that these will cancel out. And so our final answer is going to be x times the hyperbolic cosine of x. Okay, just a little bit of calculus there. This is, I think, really the most compelling reason to talk about these that I'm aware of is, and it's kind of specialized, but this power cables. So if you see like power lines as you drive along the road, and I don't know if you've ever noticed the because of gravity, the cables, the wires, the power lines kind of hang down a little bit. And if you look at that, it looks like it's kind of parabolic, that it might look like a really flattened out parabola, but in fact, those are the shape of those are called a catenary. And so when gravity acts on that and it just kind of hangs like that shape that looks like a parabola is actually a hyperbolic cosine, and it's called a catenary. And so the equation of that is given by a hyperbolic cosine of x over a, and so it is kind of parabolic because our hyperbolic cosine sort of looks like a parabola. And we're going to be told that the distance between the two towers is 2b, and we're going to try to find the slope of the catenary where the cable meets the right-hand tower. So we're talking about we want the slope of that catenary as it comes into the tower there. So we know that slope is given by the derivative, and that the x value, according to our picture there, if we kind of impose an xy axis there, the x value is going to be at b. So our slope is going to be the derivative of our a hyperbolic cosine, come back pencil, hyperbolic cosine of x over a. So we're going to get the a times the derivative of the outside function is hyperbolic sine, and we're thinking of that x over a as 1 over ax, so we'll still get that x over a, and then times the derivative of 1 over ax, which is 1 over a, and so those will cancel, the a's will cancel, and we're going to evaluate that at x equals b, and so that means that our slope right there as we come into that tower is going to be given by the hyperbolic sine of b over a. Or if you remember what that is, that's, our hyperbolic sine really involves these exponentials. So it's e to the b over a minus e to the negative b over a all over 2. Okay, that's all. Just wanted to get a chance to talk about that idea of what a catenary is. And here's a little bit more just calculus with these things. So if we have an integral of hyperbolic cosine 2x and hyperbolic sine squared, we can say, make a u substitution. U is the hyperbolic sine of 2x. That's our inside function. Du is going to be the hyperbolic cosine of 2x times the derivative of 2x dx. So our dx will be du over 2 hyperbolic cosine of 2x. That makes our integral become the hyperbolic cosine of 2x. And then we're going to call that u squared for the hyperbolic sine squared. And the dx we'll replace with a du over 2 hyperbolic cosine of 2x. And we can cancel our hyperbolic cosine of 2x's. We can pull the 1/2 out. And the integral of u squared du is going to be u to the third times 1/3. And then we also have that 1/2 that's lurking out there, making our final answer 1/6 times the hyperbolic sine cubed of 2x plus c. And the idea on the green question here, if we know that the hyperbolic sine of x is 5/3, the way to find the hyperbolic cosine is to use that fundamental relationship between our hyperbolic sine and hyperbolic cosine. That is that cos squared minus sinh squared is equal to, that should be a 1, not 0. And so then if we know that the hyperbolic sine is 5/3, we can say the hyperbolic cosine squared of x minus 5/3 squared is equal to 1. So we can get the hyperbolic cosine squared of x is going to be 1, and we're going to add over that's 25/9. And since 1 is 9/9, that's going to make that be 34/9. And we can take the square root of both sides. Square root of both sides. And we know that a hyperbolic cosine, if you remember, that's the one that looks like a parabola, sort of, but it's always positive because it's e to the x plus e to the negative x over 2. So when we take the square root, we want only the positive square root and not the negative one. And so we can call that the square root of 34 over 3. So there's our hyperbolic cosine of x. And then there's some identities that are given. When I give you the handout for this thing, I'm going to include some of the pages before there, and you should look over that. There's some, it goes through the derivatives. It shows you the graphs of all the different hyperbolic functions, which are kind of interesting. And then it's got some identities there too, some formulas. And one of those is that the hyperbolic cosine of 2x is the hyperbolic cosine squared plus the hyperbolic sine squared. It's kind of close to, I don't know if you remember from your AP prep days, probably not, we haven't done much with them, but there's an identity from there that the cosine of 2x is cosine squared x minus sine squared x. So it's very similar to the trig identities there. So using that identity, we're going to try to prove this one. So we're going to take that right side and play around with it to make it look like the left side. So we will replace that hyperbolic cosine of 2x by the hyperbolic cosine squared of x plus the hyperbolic sine squared of x all over 2. Then the tricky part is to say we know that the hyperbolic cosine squared minus the hyperbolic sine squared of x is equal to 1. So we're going to replace this 1 by exactly that. The hyperbolic cosine squared of x minus the hyperbolic sine squared of x. And then we still have that hyperbolic cosine squared of x plus the hyperbolic sine squared of x all over 2. And so we can see that we get rid of those hyperbolic sine squareds and we get 2 of the hyperbolic cosine squareds of x over 2, which then in fact is the hyperbolic cosine squared of x, which is equal to what we were trying to show it was equal to, and we have proved what it is we wanted to prove. Okay, just an introduction to hyperbolic functions.